Hello everyone, welcome to our presentation titled Supporting Program Comprehension by Generating Abstract Code Summary Tree. I am Abhijit Bhattacharjee and my co-authors are Dr. Bonani Roy and Dr. Kevin Schneider. So the motivation for our study is to help developers in their code reading activity. So in daily setting, code development activity, the ratio between reading versus writing is 10 to 1. So we can understand like how important reading code and finding the relevant part is. Also, developers have to solve issues or fix bugs in the code written by others. So sometimes they have to go into a code they are not familiar with and fix something. So they need to understand that. Also, like if someone new joins in a team and the project has no documentation or the documentation is poor, they struggle on like that. So this is also an important part in the software development activity, like onboarding in a new project. And the cost of the software is determined by the resource takes developing it. So as reading is an important part of it, we can decrease the software cost by reducing the program comprehension time. Also, recently, as the social coding platforms like GitHub are getting more popular, the collaboration is not limited to on-site teams nowadays. So now teams over the world can work on open source projects. So they work on others' code, understand it, read it, fix bugs on that. So reading activity is getting more and more important. For example, like previous year, GitHub had 56 million developers on their platform, and in total they contributed 1.9 billion contributions. And in most of the contributions, reading the code, finding the relevant parts was very important. So we want to help the open source community so that they get more good developers, as it will be easier for getting started in the project. In a regular coding environment, usually developers do not use any specific tool because it's costly to switch to a tool or switch between. So they try to use something offered by the IDE, and most of the time they just do some searching of it. So for example, if they want to do some work, so they want to find some relevant parts, so they just search it like using the default functionalities to get the parts. And we can see like most of the times it's not structured, like it's just random thing, like if the keyword is there, the IDE just provides it, so there's no order on that. Now, how developers actually comprehend code? So there are three types developers comprehend the code. The first one is top-down model. So in the top-down model, the developers has experience in the project or in the code base, so they know the high-level concepts of it. So if they have to do some work, they just go into the relevant part from like high to low code. But the problem is we don't live in a perfect world, so people leave teams, new people join the team. So many times people have no idea about the domain, so they have to go to low level course and one step by step they just build up the high level concepts to figure out what they need to do for accomplishing a task in hand. And there is the last one, it's integrated. So this is kind of mix between top down and bottom up. So many times developers have idea about some part of the code base and not others part, so they just try to mix the top down and bottom up model for that. So in existing studies, a lot of studies is going on using dynamic call graph or execution traces and static call graphs. So different kind of abstraction technique is being applied in the dynamic call graphs generated from the execution traces to help program comprehension activity, but the dynamic call graph have some difficulty because we need to run the code and it's limited to the user scenarios we run the execution traces for. So recently the program comprehension work is being focused using a static call graph as it has some benefits compared to dynamic call graph. So the recent studies also focused on that. They try to build abstract cluster tree uh, using the static call graph, like from the execution parts of the static call graph, and also like to name different artifacts of the source code, like different IR methods are being used. So to figure out what part of the code can be used with what IR methods to properly abstract a code base. So we are thinking where we can contribute. So we came up with 2 points. First one is to reduce developers program comprehension time, to understand overview of the project, and the second one is to help them accomplishing the task they have in hand and do it faster. So we started uh, from the what we have in the literature and did some steps, added some steps and modified some steps to make a new tree. We call it abstract code summary tree, and the benefit of it is it is usable in a daily coding activity compared to the other related proposed techniques. They we find are a bit difficult to explore, so we remove the issues in the existing study and added some more information in addition, so that the tree becomes useful in development activity. So first we get the Python files, as our subject system was in Python. Then we generate the abstract syntax tree, and from the syntax tree we can get the relationship between different methods. We call this caller callee relationship, and from that we simply build a static call graph. And this call graph has all the execution paths, so we run a DFS algorithm, a modified DFS algorithm to find all the execution paths. So here we see the execution paths, and these paths are the building blocks for the abstract code summary tree. So previous studies used Jaccard similarity matrix, which simply accounts for the content of two pairs, not their sequence, but we find that it is important to account for the sequence also. So we used a different metric. We call it's called strike match. It accounts for the content and similarity, the sequence similarity, and then we cluster the tree, use the execution paths using the distance matrix, and we build the cluster tree, and then we apply some thresholding to make the tree more usable, like so there will be less nodes, and we remove the redundant nodes, and we provided what is important. So by this way we get the abstract code summary tree. Also in the nodes we attach to information we call node summary and execution patterns. So in the later pages slides we'll discuss that. So here we'll see an example of the FNACS tree. So we build a simple calculator program which has different operations, like it takes input to numbers, validates it, and just decides which operation we want to do. So here we see two execution paths, EP01 and EP1, EP0 and EP1. So we see they are just initializing, deciding which operations to do, and they do the operation in the with two numbers. So we see it's doing multiplication and addition. So in the abstraction node we see 5 keywords, we apply tf-idf on that. So an7 it says some keywords, and we see there is the keyword add, multiply, and to. So we see it's kind of the 5 keywords kind of summarizing the execution paths. Similarly, if we move forward, we see as we have more execution paths and we have different information, so our technique is just bringing out the different information and ignoring the same one. So for example, if we see the n node 10, we see it's saying add, divide, mod, multiplication, and subtract. So if we see the ep0 to ep4, so these 5 execution paths, so they are just all of them is kind of same, but they are doing different operation, and our node title is saying this operation. So we see it's kind of abstracting these 5 execution paths. Also, and now if we like as we go building the cluster tree, we see that it's trying to bring up the new changes. So now now we see this is a agglomerative clustering tree, but we added some information on that, and we did some modification in the tree based on some thresholding to remove the redundant nodes and make it more useful. So we call this tree as abstract code summary tree, as it is summarizing the source code in respect to static execution dependencies. So now we'll discuss how we get the node summary and execution patterns. So the a node has execution paths, and the execution paths has methods. So we collect all the comments of the methods of the node, and we summarize that using text track algorithm, as it doesn't require previous training, because it tries to like get some similarity between the text, and so it doesn't need previous training, so it fits very well with our purpose. So now we get the execution patterns. So we have collection of execution paths, and they have repetitive patterns. So we applied applied sequential pattern mining algorithm to find the patterns. So we call them as execution patterns. So we attach these two information with the nodes. So now we we measure how effective this our ACS tree is compared to a real-time development scenario in the opinion of experts. So we did change the similarity matrix, we reduced the nodes in the tree, and we developed a prototype for the developers so that they can check it out themselves and let us or evaluate what they think. We collected expert opinion on their subject system, and we have two usage scenarios. So the first one is whether they can get an overview of their system using our tool, and the second one is whether if they can use our system or our approach in doing a specific task. So these are the two research question or usage scenarios we have. So in the study, we conducted the study on the Site Data Manager project. We invited their developers to participate in the study. We built the ACS tree on the Site Data Manager code base, and 3 of the participants evaluated our system for the 2 use cases. In the end, we also they also answered some open-ended questions, so we collected their feedbacks and opinions. So we noted their comments and feedbacks. while they were doing the two scenarios, and we find that they were able to relate some high level features of the system with from the node names. And when they find the node summary, they are able to get more understanding about what the keywords hinting. And they suggested that searching by the keywords in the tree can help them, instead of just randomly going to the code base, they can have a guided way to explore that. And also they appreciated as they can search by keyword in the methods, and the system can highlight the nodes. Also, one of the developers suggested they can check out different places they need to look when they want to change something, by checking the execution patterns and execution paths, and highlighting the nodes affected by a specific method. Now we will see the application we provided to the developers. So in the left we select the subject system, we can search with keywords, and then the nodes which had the keyword in the method name, they will be highlighted, so developers can explore the tree guided way. So in between we have the ACS tree. Developers can go deep in different from different nodes, and they check out different node contents by right clicking on that. Here they can see some execution paths of the node. Here are some of the details of the node, and here are node summary, so it's natural text extracted from the comments and the execution patterns. So in future we plan to integrate GitHub with our application, so that developer can export their repository from GitHub and explore the code base using our approach. As in real development environment, not every methods are commented properly, so we have some plan to add automatic code comment generation techniques, and that will help the node summary perform well. Also we'll provide some documentation export features, so that developers can export some of the parts of the tree and use it in their documentation. And as suggested by participants of the study, we will add search by file name and classes in addition to methods. So in summary, we provided the general text summary for abstraction nodes. We also added execution patterns for them, and we built a way to we had an automated way to build ACS tree from source code, and we developed the approach to reduce developers onboarding time on a new project. And also we created the approach to help locate relevant method or files for a task in hand. So we have the application hosted at acpc.users.ca. Please visit that and check out. Thank you.